Hello, everybody. Welcome to, hopefully, episode 2 of PhD Live. I'm talking slow because I'm loading up the video to see if I can actually hear myself talking or not. Yes, okay, we are, in fact, actually live, which is very exciting. So, today, what I'm going to be talking about is, well, it's been a very exciting week on my project so far since I last spoke to you on Monday. I've had 2 meetings with my supervisor. I've sat in on a whole bunch of different classes, some of which I wasn't even expecting until like the day of. But I think definitely the thing I'm the most excited about is the list of papers that I now have to read that are sort of representing the first stage of my project. And I think I'm going to focus today on sharing a little bit about these papers, well, the small amount that I've learned so far with you. So, one of these papers, actually, I'm just going to try to pull it up. Um, One of these papers is sort of a review of recent developments in neutrino mass physics. So, when I'm talking about neutrino mass physics, as it turns out, and I didn't know this until a couple days ago, there's a lot more things we're interested in finding out about neutrinos than just their mass. Um, so, because for one thing, measuring the mass of neutrinos accurately is a pretty steep physics challenge that even the next generation of experiments that we're developing on they might place tighter bounds on it, but we're pretty far away from ending up with some single value for neutrino mass. Um, but what could apparently be somewhat easier to find out, or we can find out somewhat sooner, is the order of the masses of the three neutrinos. So as I talked about last time, in the standard model, there's 3 different flavors of neutrinos. We're pretty sure there's just 3, and not more than that, which is something I can get into on another session. But one thing that we're not sure about is which ones are the heavier ones and which ones are the lighter ones. Um, this is further complicated by the fact that when we're talking about these particles, we're talking about quantum physics. We're talking about objects which don't just exist in classical states where something has a defined position, speed, even properties like charge, or how something is spinning. We're not talking about classical properties. We're talking about quantum properties, which can exist in superimposed states. So a neutrino of one of those 3 types that we talked about, so either the electron neutrino or the muon neutrino or the tau neutrino, uh, these are just sort of example pure states in physics language. They're eigenstates of the neutrino field. And it can exist in one of these pure states, but it can also exist in combinations of these states at any given time. And as it turns out, for neutrinos, um, I should really do a review on quantum physics because I know not everybody necessarily has a background in that. Um, but yeah, okay, no time like the present. Let's do a little bit of quantum physics review. As someone mentioned last time, I did need another light source, and I now have another light source. So I'm going to try to switch this over in such a way that my big hair doesn't cast a big shadow all over my page here. Uh, okay, so yeah, this is what everybody was seeing last time. I get it. It's a lot of hair. Now we have light. Yeah, okay, this is definitely objectively better. So, um, quantum physics. Let's talk about it. I like how I started that sentence kind of outlining what this session was going to be about, and then ended it with starting a session on something completely different. But this is a work in progress. Uh, to really talk about what makes quantum physics special. Is that readable? Yeah, I think that's readable. I probably need like marker pens too. Yeah, I'm gonna write that on my list. This is my list of improvements that I need to make for the show. One of them is that I think on this welcome screen over here there should be some sort of like big PhD Live logo, and maybe my name like in a slightly smaller font under that. But for now, yeah, I don't have that yet. But yeah, okay, marker pens is going on the list too. Uh, so quantum physics. The the main thing that separates quantum physics from classical physics, as I understand it, is that uh, the values that physical parameters take are no longer numbers. In classical physics, everything is a number. If you have say like the traditional high school physics problem of a man standing on a cliff and throwing a tennis ball or something off the cliff, um, and you have to find the trajectory. That's the first classical physics problem that anybody encounters. Uh, at any given point along this trajectory, you can know certain things about the ball. You can know its height, what's its vertical position. You can know its horizontal position, and you can know its velocity in both the vertical and horizontal directions. Um, so there's sort of four numbers, and if you know those four numbers in this very simplified two-dimensional problem, you know everything you need to know about the dynamics of the ball. Um, and that is fundamentally true throughout classical physics, where no matter how complicated the system is, you can narrow it down to some set of numbers that describe everything that's going on. If you know what all those numbers are, and you know the equations of state that sort of describe the system, so in this case, Newton's laws and like basic earthbound gravity, then you can predict everything that is ever going to happen to the system, and you have perfect knowledge. This was the state of physics in the late 1800s. Um, Quantum physics differs in that you can't have perfect knowledge about a system. That's fundamentally not true. So when we talk about something like a fundamental particle, so I mean, I'm going to be talking about neutrinos a lot, so might as well have it be a neutrino. This is supposed to be the Greek letter nu, by the way, in case I didn't make that clear before. Yeah, nu for neutrino, I guess. Someone's idea of a joke. But for a quantum particle, for anything that's small enough for its quantum effects to be noticeable, which is, I know that's kind of vaguely defined, but it very much is a size thing, where every object has a size at which quantum effects become noticeable, and you can sort of calculate this based on how much energy the object has. You can arrive at a frequency of sort of a corresponding wave that corresponds to that object, and from that wave you can get a length, the scale at which quantum effects become noticeable. For something big like a person, this scale is so much smaller than us that we would never notice it. But for something very tiny like a particle, it is at the scale of the particle, if not much larger, and so quantum effects become very important. This is sort of the idea that when you look closely enough, particles and waves are the same thing. This is all the same idea. So a particle like a neutrino, we can try to measure its position, but when we try to measure its position, we're not going to get some, well, let's say that this is the axis of possible positions. If this was a classical object, we could measure its position really precisely and get something like a line here that just very directly points out the position. In quantum physics, we get something more like a probability distribution. So we're almost completely sure that the object is not over here or over here, but in the middle, there's sort of a likelihood of it being anywhere in this range. And most likely it's in the middle. This is a one fundamental rule in quantum physics, is that the average of the possible quantum states corresponds to the classical state. I forget what that's called, but there's a name for it. And we can see that here. Yeah, yes, there's this probability distribution. Right in the middle, right at the peak, is the classical state. But the quantum object doesn't actually have to be at that classical state. It can be somewhere nearby. And this is just one variable. We've been trying to measure the position. If we try to measure another variable now, like how fast the particle is moving, we can get either one of these variables individually as accurate as we want. So this, let's call the width of this little mountain here that is the probability distribution. Let's call that delta x, just the width of this peak. We could do another measurement for the velocity or the momentum of the object, and we could get another peak with another width, delta p, for momentum. But we can't get either. So we can get either one of these as small as we want, but we can't get them both as small as we want at the same time. And this is Heisenberg's uncertainty principle. The idea that this product, delta x times delta p, this has a minimum value, which is proportional. Ooh, this is something I should remember from an undergrad, but I don't. Just gonna Google that real quick. It's definitely something with an h bar. There's always an h bar in these sorts of equations. Yeah, of course. H bar over 2. I guess I really just could have made up any constant here because it is a constant. This is a physical constant that we eventually were able to measure, that sort of represents the scale of uncertainty of quantum physics. This was pretty vague, but this principle of not being able to measure things perfectly has sort of another interpretation, and the way to think about that I think is better described by looking at a slightly different example, and then I'll come back to this one. This is sort of a more quantum-y example, and by that I mean it's rather than just talking about a particle, which is at the classical scale, and then saying, okay, now it's at the quantum scale. Let's talk about an object which is necessarily already at the quantum scale, like an atom. So an atom, a really simple hydrogen atom, has a proton in the nucleus, then it has an electron kind of, well, not really orbiting around, but it's around the outside somewhere. And we know that a thing that we can do with atoms is put energy into them. This is high school chemistry, that there's different shells that the electrons can live in, and if you put enough energy in, you can get the electron to go from this innermost shell, the ground state, up to this shell. Or if you put a little more energy in, you can get it to go up to this shell. And by doing so, the atom now has more energy. You've stored more energy in it, and later on it could release it. The electron could drop back down a shell, and in doing so, release a photon, a gamma ray, that has the amount of energy that came out of that. So energy is conserved in this whole system, but the electron is bouncing around between different shells. What these shells really are different quantum states that the electron is allowed to be in. This is a little bit easier to see than the example of like the position of the neutrino, because here there's a discrete set of states. I just drew 3. Really, it goes out to infinity, but they're spaced like the whole numbers. There's infinite whole numbers, but they're distinct from each other. There's a lot of numbers in between, and these are individually marked and stand out. Whereas when you talk about the position of an object, that's a continuous spectrum like the real numbers, where you can zoom in and more between any 2 points and find another number, but that's not the case here. There's this limited set of states, and we know that the electron, when we measure it, must be in one of these or the other. What am I trying to get to here? I guess the point that I'm trying to make is to draw an analogy between this continuous case of having a particle that lives in some region and we'd like to know where it is. And I've said that in quantum physics you don't exactly know where it is, you know some distribution. What does it really mean to measure a distribution? Obviously, when you look at a single electron, you don't see this distribution. If you look at an electron just once, you do see it in some location. Maybe it's here, maybe it's here. This idea of a probability distribution says that when you look at a lot of electrons that have been prepared in the same way, you're repeating some experiment, or maybe a better example is sending a lot of light through some diffraction grating. Any individual photon particle is going to end up at some location, but as a whole, the whole, this sort of depends on whether you interpret it as a particle or a wave, but interpreting it as particles, the particles have this probability of ending up somewhere along this distribution. Most of them are going to end up at this area where the probability is highest, but some will be spread out in the lower areas, and as you do more and more, you eventually approach this distribution. This is true of the atom as well, because even though you may measure an atom to be in one of these individual states, so maybe the electron is in the first shell or the second shell or the third shell, and you measure somehow the energy of the electron in the atom, and you say, oh, it's in the second state. But if you prepare a whole bunch of atoms in the same way, it's possible for them to be in a superposition of these states, where until you measure it, it's really some combination of these with some amount of weighting of each that determines the probability that when you measure it, you get this one or this one or this one or something else. Much like this, it's a probability distribution. It's just that here the probability distribution is not a continuum. It's some combination of 1, 2, 3, and so on. Maybe that probability distribution is most likely this one, less likely this one, and so on. And the only difference between this probability distribution and this probability distribution is that this is over a discrete set of values and this is over a continuous one. So this sort of sums up the general properties of quantum mechanics, which is that systems don't have to just be in one state. They have a set of possible states, and they can be in any combination of these possible states. They can be prepared in that way, but when you measure them, it still isolates to just one of these states, and that's the collapse of the wave function. It's sometimes referred to that way. So getting back to the neutrino idea, when we talk about those 3 different types of neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino, what are these electron, muon, tau properties? Really, this is what I'm going to call a number called lepton flavor, and this is just a quantity that tells you what type these particles are. It's sort of similar to talking about electric charge. you have some amount of electric charge, and that determines whether you're a positive particle or a negative particle. This is a little trickier because it has three different sort of varieties rather than two, but conceptually it's the same. There's some number that tells you which flavor the neutrino is. But that number is totally different from measuring the mass of a particle. That's really a separate quantity that a particle can have. So when we talk about these quantum states that can be in superpositions, whether something is in a superposition or not really sort of depends on what you're trying to measure. So we can think of these electron, muon, mu, and tau neutrinos as sort of like three independent axes. And a pure electron neutrino state is somewhere here on the electron axis. That's 100% an electron neutrino. If you measure it in such a way that you can tell which type it is, you're guaranteed to get an electron neutrino. A muon neutrino is somewhere here, and a tau neutrino is somewhere here. But you can very easily have any superposition anywhere in between, so that when you measure it, there's some probability of getting one of these three. But the states that so we also know that there's some three masses for neutrinos, some three possible mass states. They don't necessarily, as I'm gonna talk about, correspond exactly to these three particles, but we still know that there's three because the fact that there are three different flavors of neutrinos sort of means that neutrinos have three inherent degrees of freedom to them, like it's a three-dimensional internal parameter space, I guess is the right way to put that. And because of that, when you're talking about the mass, there's still sort of three-dimensional parameter space corresponding to the mass. And it makes sense that there would be a spectrum of three different masses that the neutrino field can take on. We're still working in the same coordinate system that describes the flavor, the lepton flavor, but the vector in this vector space that corresponds purely to mass 1, that could be somewhere out here, some linear combination of these three. I think actually it is actually quite close to the electron vector, we think, but in theory those three mass eigenstates could be anywhere, as long as they form an independent basis of the space. They're pointing in different directions. They're not all pointing along the same line or plane or something. And just as we can think of this mass state as a combination of the three flavor states, we can invert that and think of the electron state really as a combination of three different mass states. So if you measure if we had a foolproof way of measuring the mass of an electron neutrino, it wouldn't be the same every time. It would be one of these three states, which there is a sort of weak correspondence between these three. Like we know that each of these states is pretty close to one of these flavor states. So really, if I drew these vectors, I should draw them in such a way that one of them is pretty close to the electron state, one of them is pretty close to the muon state, and one of them is pretty close to the tau state, but not exactly. So one of the most interesting experimental goals right now is to find out what these three mass values are. That's what I was saying is pretty challenging to do, to measure these exact mass values for reasons that I don't really understand yet. But achieving that is further out. What may be less far out is figuring out the order of the mass states. One thing we do know is that the mass, the first mass state is less than the second mass state. We know that. But what we don't know is whether this third mass state is greater than both of these. So that it could be that this could be the case. There's sort of two options here. You could have mass 1 less than mass 2, and then mass 3 is even bigger than that. Or you can have mass 1 is less than mass 2, and mass 3 is less than both of those. These are the two options that we've narrowed it down to based on the experimental data we have so far. But which one of these it is a pretty significant difference for the overall properties of neutrinos. And these are referred to as the normal ordering, NO, because all the other families of particles that I talked about last time do this. The electron is less massive than the muon, is less massive than the tau particle. The quarks, which were in those three families, also went from lighter to heavier. This would kind of be what we would guess intuitively. But as of now, this inverted ordering is also totally possible. It's definitely one of the two, but we experimentally aren't sure yet. And these papers that I'm now finally going to start talking about a little bit will give a clue as to the experimental status of figuring out which one of these is the case. Let's switch back to regular video now. Okay, so this is the second paper. I don't want to talk about this paper yet. It's quite a long paper. It's 62 pages. It's definitely up there. I started reading this one, and I've got some notes on it, which I'll take a look at now. So one thing I really like to do is take LaTeX notes as I'm reading papers. I started doing this, I guess like 2 or 3 years ago, when I had a few classes in undergrad where you were required to use LaTeX to take certain like project notes. Yeah, shout out to ECE Capstone. But it's a really good system. It worked well for me in cases where I don't necessarily need to write a lot of equations or draw diagrams, because those are in the paper. I'm just sort of taking mental notes as I read. And in a few cases I've tried it for classes too, and it can work pretty well. I think you need to be a fast typist, which is something I've practiced, but if I can keep up with the lecture and sort of live tech the notes as I go, it's pretty nice, because I end up with, in the end, instead of handwritten notes, I get this kind of crisp version that's very easy to send to other people or look back on later. And also, I'm not killing trees, so that's kind of nice too. Yeah, it's a really compatible medium. So for reading papers, I've been taking these notes, I guess roughly in like lecture style format. Oh, here we go. Ooh, another thing from my list is I really need a way. So I have keyboard shortcuts, which is like Windows left and Windows right, to switch my tabs from like the left side of my screen to the right side of my screen. I can also do the top and the bottom, but I'd really like to be able to do the top right corner and the bottom right corner. back when I had Fedora Linux, there was some app that would pull up like a little grid in the middle of the screen, if anybody remembers that, and you could, it was really efficient because then you could sort of use your arrow keys and trace out of like a 6x6 grid of options. You could trace out the size of the window you want, just typing, and then it would put the window there. So you could put it in the corner, you could put it in the middle, and you could really tile your screen with all sorts of stuff. But I haven't been able to find the Ubuntu equivalent of that. Yeah, that's going on the list. Yeah, because that would really help, especially since I'm doing this like just showing you the right side of the screen thing. If I could fit two things there efficiently. What's the word for that? Yeah, tiling, I guess. Tiling to corners is on the list. Because instead, I kind of have to drag it like that, which just feels like I've regressed 100 years with technology. At least it snaps into place. That's pretty good. Okay. Neutrino mass ordering from oscillations and beyond, 2018 status, and future prospects. So, I'm sure this is going to describe it a lot better than I just did. Current available tools to measure the neutrino mass order, and that's kind of the key point of this, because there's not just one experimental way of doing this. People are doing accelerator experiments, specifically long baseline accelerator experiments. So this is pretty cool. What's it called? One thing I'm really going to make an effort to do is like memorize the names of all the experiments that have anything to do with the theory that I'm doing. It's at Fermilab. Oh, Dune, that's right. Yeah. So the Dune experiment is just a really cool idea. So Fermilab has been there for a long time, of course, in Illinois, big particle accelerator facility, and mostly when particles are accelerated, we do it in circular structures because that has the advantage that you can't with a straight line beam, you kind of have to start the particle at one end and just accelerate it once and hope it, there's only so much speed that you can get it up to by the time it gets to the end of the pipe. But with a circle, you start sending it around and it gets back to the beginning again, and you can keep accelerating it for as long as you want. I mean, you start running into other limitations where the particles start radiating energy because of the circular motion, and you also sort of run into the limits of the faster it goes, the stronger a magnet you need to keep pulling it in a circle. So there's still limitations, but these circular structures have been the standard for a while. But it's kind of ironic that neutrino experiments kind of bring it back to needing a straight line structure, because what we want to do is take these neutrinos, which are produced in particle collisions in some of these accelerators. Like it's pretty easy to make a neutrino source. That's not the challenging part. The challenging part is measuring the neutrinos, because they interact so weakly and they're neutral. And the other challenge is, well, when you do detect them, what are you trying to measure? What we're interested in measuring here, because we know that the neutrinos have these three different states, but they're able to oscillate between them, is you need to give them the time to actually undergo that oscillation, because it is a time-dependent thing. The further a neutrino goes, the greater the chance that it will oscillate, and you can measure that distance with greater precision, and from that get information about the neutrino mass. So what they've done now is at Fermilab. This is really an overhead summary because I don't know that much about it, but they take this beam. Okay, they didn't say it here yet. Intense high energy beam of neutrinos, and rather than sending it out sort of straight along the Earth and then measuring it, they send it downwards into the Earth at an angle. So straight into the dirt, into the bedrock, and then they go to South Dakota, and because the Earth isn't flat, it comes up again. It's really good proof that the Earth isn't flat. Is you send this laser beam really downward, and then you go far away, and it comes back up at you. So they go to South Dakota, they build a big detector there. I mean, I gather that's tricky because they have to know really precisely where it's going to come up again, or maybe they can angle the beam. Maybe they build the detector first and then angle the beam to hit it. That would make a little more sense, I guess. But by the time it gets there, it's passed through 800 miles of stone and earth, and the fact that it's interacting with matter along the way, which has electrons in it, makes it more likely for the oscillation transitions to happen, apparently. So that's an advantage too. And these are called long baseline neutrino experiments because rather than, as is the case in so many experiments, you're accelerating particles, you're doing a collision, and then you're immediately measuring it like as quickly as you can, because so many of these particles will be very hard to find if you don't put your detectors all around where the collision is happening. But the opposite strategy is needed here. So, notes I took. Let's see how good my notes are now. Oh, I don't know why I'm pulling up the LaTeX version of the notes. You probably don't want to see that. I can pull up the whole point of LaTeX is that is that you end up with a PDF of the notes. Yeah, there we go. I wrote this, and I'm proud of it. Neutrino oscillations and masses are the first known departure from the standard model because they allow for mixing and CP violation in the lepton sector. I underline that because I'm not super clear on CP violation. It's a symmetry that shouldn't be violated in the standard model, but is, it seems, by neutrino oscillations. That aside, the other interesting things that we want to know about neutrinos are what sort of spin character. What sort of I guess it is a spin property. Basically, whether neutrinos are their own antiparticles or not, because when we thought they were massless, it would sort of make sense for them to be their own antiparticles, which means that it's possible for them to annihilate each other. That's not possible for like electrons, for example. You can't have an electron go up to another electron and collide together, and they both go away and you get other stuff. That's not allowed because the overall lepton number, that's a quantity that has to be conserved. But photons, for example, light, photons can collide and annihilate because they don't. There's no conserved quantity that they have there. They're kind of neutral in most senses, and that allows them to annihilate each other. So Majorana neutrinos would be neutrinos that are their own antiparticles. And this actually leads into the Neutrinoless double beta decay that I'm going to be studying, because the only way that Neutrinoless double beta decay can happen is if those two neutrinos that are released can annihilate each other and produce. They can produce just energy or light or other decay products. Doesn't really matter, but you end up with zero neutrinos, and that can only happen if neutrinos have Majorana character. CP violation, skipping that for now because I don't really know what it is. Absolute scale of neutrino masses. So that refers to going and measuring, like, literally what is the mass of the neutrinos. We don't know how to do that. That's probably the hardest one on the list. But the order of the neutrino mass spectrum, this question of whether it's the normal order 1, 2, 3 or the inverted order 3, 1, 2. So how do we know what we already know about the neutrino mass order? We measure neutrinos from the sun all the time. So the sun is a big nuclear reactor, and it's going through these double beta decays all the time and producing lots of electron-type neutrinos, almost exclusively because, as muons and tau particles are less stable, so it's way less likely that you'd find them, especially in a place like the sun where there's a lot of pressure. And I think there's an argument for why in that kind of environment you're less likely to find these exotic particles, because the added temperature and likelihood that they're going to collide with something else makes their lifetimes even shorter. So we can assume that the neutrinos that are coming out of the sun are all electron neutrinos to start. But this oscillation happens as they fly through space. And I had a great meeting with my supervisor yesterday, and he started trying to explain sort of why this neutrino oscillation happens. I think I can try to repeat what he said if I switch back to the downward cam here. So we just talked about before how this neutrino, I'm going to use actual quantum notation here, which is this, I need a better pen, here we go. The electron neutrino pure state, the pure electron neutrino, is really some combination of the three possible neutrino mass states. Without knowing what these numbers are, except that alpha is bigger. We do have constraints on these numbers, but alpha is probably like 0.9 or something, because the electron neutrino is mostly the first mass state, and then these are smaller. There we go. So we can envision sort of a packet of electron neutrinos leaving the sun. They're emitted, and they start heading towards Earth, which is not to scale. There's this combination of the three mass states, but at the beginning they're all on top of each other. I could do them. Well, I'll just ignore the third mass state. Let's just say it's these two, and these two states are right on top of each other at the beginning, because all the neutrinos are being emitted at the same time, at the same temperature. You know, they have a pretty uniform distribution as time goes on. But these two mass states ultimately have different properties because they have different masses. And for a neutrino, the mass that it has directly corresponds to how much velocity it has, with some given amount of energy. And the neutrinos, as they're going through space, they are being affected, I guess, by other particles still at this point. And there's also the velocity that they got emitted from as a packet from the sun with. That energy is, you can imagine that it's distributed out evenly among all the neutrinos. But the mass state, which has less mass, which let's say we know, which we do know, that the mass 1 is less than mass 2. Then it follows that mass 1 state will move faster than mass 2 state, because it's lighter. So as time goes on, the separation is going to happen between these two packets of neutrinos. And as time goes on, this region, let's say we're looking at this packet of neutrinos, we've sort of frozen it in time. and this is composed of the mass 1 state, the lighter ones, and this is composed of the heavier ones. When I say ones, I'm not talking about individual neutrino particles. This is sort of a superposition of neutrino field quantum states. Everything here is purely in that mass 1 state. Which, by the way, because the mass 1 state is a superposition of electron, muon, and tau neutrinos, there's some mixing that goes on between the different neutrino states here. But for now, nothing interesting is happening here. And nothing interesting is happening where it's all the pure, heavier mass 2 state. But in between, in the regions in space where both of these are present, but in different ratios now than they were at the beginning, apparently this is where the conditions are right for the neutrino oscillations to happen. For the combination of neutrinos of the neutrino mass states to balance in such a way that you end up with majority muon neutrinos rather than just the electron ones. And so by the time it gets to the Earth, where you started with all 100% electron neutrinos, by the time it gets to the Earth, you have some combination of muon ones too, and I think some much smaller amount of tau ones as well. But so when they talk about in this paper here, the solar mass splitting, this is the quantity that's observable from neutrinos from the sun undergoing this oscillation between electron and muon type neutrinos. Just the way the math works out, we unfortunately don't get the mass difference between mass 1 and mass 2 because of this. We get the difference between their squared masses, which is still really useful. It gives us a lot of information about the difference. I'm going to switch back to the main camera. It tells us a lot about the difference in magnitudes of the two masses, but it doesn't necessarily tell us, like, if we know this delta mass squared, we can take the square root, and then we know what delta mass is, but we don't know the sign. It could be either way. So just because we figured out the difference between mass 1 squared and mass 2 squared doesn't mean we know which one is bigger. We can also use atmospheric neutrinos to measure the difference between the mass 1 and the mass 3, and we get these two values, which imply these different orders. It's the only reason we know the order between 1 and 2 is from these matter effects that happen at experiments like Dune, or actually I don't know if it happened there yet, but some neutrinos that we measure have passed all the way through the entire Earth from the other side, and then we get a lot of information that way about the difference between those two masses, because why is that the case? I think maybe I'll explain that later. I thought I did. I don't know. I'll come back to that. So then what else do we have here? Yeah, the fact that the neutrino mass eigenstates are superpositions of the weak eigenstates, which refers to those three different flavors of neutrinos. Oh, this is interesting. So, from the other way that we measure interesting stuff about neutrinos is from cosmology. So, cosmology is the study of the very furthest away regions of space and the large scale structure of space, and the what was going on at the birth of the universe. It's the largest and oldest possible scale of cosmology, of astrophysics, is cosmology. And one really essential tool of cosmology is the cosmic microwave background, which is the signal of microwave radiation that we get from space. It's not coming from any one object in particular, it's everywhere. And it's very uniform. We can look in any direction and we get this distribution of microwave radiation that clearly isn't coming from any one source other than the Big Bang. It's the remnant radiation from the stuff that happened in the really, really early universe. Um, but it's not exactly uniform because there were some interesting, mostly quantum effects that happened at that very early stage of the universe that led to some areas of higher density, some areas of lower density, and there's an incredible amount of information to be extracted about the particles that existed at that time, which included neutrinos, how they were interacting with each other, what their properties were. This is all reflected in the shape of the cosmic microwave background. Um, neutrinos, neutrinos now are so hard to detect because they don't really interact with much. They stream freely is the cosmological term for it, apparently. And whereas for much of the early universe, there was a time when everything was so hot and dense, for example, that there were no atoms. All the electrons had way too much energy to be trapped in an atom. They were going around interacting with stuff all the time. And then eventually the temperature decreased enough that this phase transition happened where the electrons started getting stored in atoms. There were a lot less free charged particles floating around interacting with things. And that's the moment that light starts being able to permeate through space longer, and eventually everywhere there are light signals that are sent out that are statistically likely to survive to this day that we can see, whereas prior to that, any light that came out from some interaction was more than likely going to hit some other particle and get absorbed, and not all that light is gone. Neutrinos, because they interact so weakly, it seems that they would have decoupled from that really hot sort of plasma setup much earlier, so much at a higher energy, and so you have all these neutrinos that for a while were still interacting with lots of things because everything was dense enough that it was likely. But then a transition happened and the neutrinos weren't interacting with anything anymore. But this transition happened before the stuff that caused the CMB to be released happened. And so this is good because it means that the properties of neutrinos will have had a significant impact on the properties of the CMB, and so that means that we can measure the CMB and get some information about neutrino properties from that. One idea, which apparently isn't quite possible yet, but seems like a really good idea when it is possible, is that if there's three different neutrino masses, and if they're different enough from each other, which is something we don't really know yet, because even though we now have some idea of the difference between the neutrino masses, we don't know the absolute scale. It's like saying you have three people, and we know that they're like an inch apart in height from each other, like 0, 1 inches, 2 inches. But you haven't been told whether they're adults or whether they're babies. And for a baby, maybe it's a pretty noticeable difference whether they're, I don't know how big babies are, 18 inches, 19 inches, 20 inches. That's a more noticeable difference than an adult that is 5'9", 5'10", 5'11". So it may be that these neutrino masses are small enough on the same scale of the difference between them that those masses are actually quite different. But it's also possible that they're different from each other, but they're all large enough that it's not so comparatively noticeable. If the first thing is true, if the difference is noticeable, then this decoupling from the really hot early universe could have happened for the three masses at noticeably different times, and we could look at the CMB and see that, and see sort of the three different mass decouplings happening, and from that get information about them. But we don't know if that's possible until we know more about the overall scale of neutrino mass. I already talked about Neutrinoless double beta decay. Yeah, so that's pretty much what I've read from this so far. That there's these three different ways of possibly figuring out the neutrino mass order. One of them is the neutrino oscillation stuff, so more precise studies of both solar and atmospheric neutrinos, and the ones that we can generate on these ground experiments, the long baseline experiments. This sort of controlled oscillation can give us some information about the ordering of neutrino masses. The Neutrinoless double beta decay can also give us some information because, only if neutrinos are Majorana particles, because otherwise that interaction can't happen at all. But if it can happen, the way that it happens can give us some information about neutrino mass. And then finally we have these cosmological observations that we can look at the very early universe and observe the effects that neutrinos had upon that early universe, and so learn more things about them that way. That was all in the introduction of those papers, so I think the rest of it is gonna really ramp up. I'm definitely not gonna get to the rest of this. I'm not really even gonna start this paper in this stream, but the general idea of where I'm going next is taking data from those three categories: so oscillation experiments, Neutrinoless double beta decay, and cosmology. Each of these experiments can provide bounds on what the absolute neutrino masses are, the order, and the spin, and the Majorana characteristic, whether it's its own antiparticle or not. All of them can give information about those things, I think. But wouldn't it be nice if, rather than expecting any one experiment on its own to give all the answers, you could combine the information from all of them, and do it in a statistically valid way, and then make predictions. And so that's what I'm going to be trying to do somewhat for the first part of my project. But some people have already made some pretty good progress on how to do that. So yeah, I need to read this paper pretty much, and then I'll come back and I'll talk more about it. I don't think anyone was asking any questions today. I also didn't advertise this on Facebook, so that could have something to do with it. I got 4 viewers. That's pretty good. Oh no, so yeah, okay. Christian said, "Yeet." It's not really a question, but I'll take it. Oh, no, I did have a couple questions left over from last time that I did not get a chance to answer yet, so I will do that. One question I was asked, why I picked my PhD, and also like why I chose to do a PhD in this. I think I'll answer the second question first, which is why did I choose to do a PhD? I think that physics research is certainly, like many things, something you can only learn how to do through practice. You can't. Nobody just goes out and starts doing research and becomes the best researcher, or even a good researcher. You have to work at it, and that's kind of the whole idea of a PhD. Is it provides the environment for you to learn how to be a researcher and make mistakes kind of in a risk-free way. Like you have the time as a PhD student to go down the wrong path a few times and learn some lessons from that. And you also have access to supervisors, professors, older students, all these role models who you can go to and ask if you're on the right track. I mean, that's always true as an adult, but as a professor, you may be the most senior person in your department doing what you're doing, and then I imagine it's harder to find people to go to for advice about stuff you're struggling with. But as a PhD student, ideally, you have that option, and you know it's important to find a supervisor who provides that support for you and is willing to answer your questions, which mine certainly is. And I'm lucky because I've heard horror stories from other people, but everything's going great for me so far. The first part of the question, why did I choose this topic in particular? I didn't choose this topic specifically. I knew that I wanted to do a PhD in ideally theoretical physics, maybe theoretical particle physics, but beyond that, I really had no idea. When I applied to programs, and sometime I'll do a full 2-hour rant about the application process, but tonight is not the night for that. I had to write a lot of descriptions about what my research interests were, and it often depended on the school, kind of what things were professors at that particular school doing that I was interested in. UCL is incredibly strong in particle physics, especially experimental particle physics. They do have, as I'm doing, theoretical particle physics too, but it's very linked to the experimental side. Like they don't have a presence in, I don't know, string theory, for example, which is also a type of theoretical fundamental physics, particle physics in a way, but it's different in that it's not so close to actual experiments that people are doing. Sometimes this is referred to more as phenomenology, but I think it differs in that phenomenology is in particle physics making sense of experiments and guiding future experiments. So certainly this sub project that I'm doing right now is an example of phenomenology, where I'm looking at data. I'm looking at data that might be collected in the future by future hypothetical experiments, and trying to figure out how that relates to theory. But I also will have this other side of trying to perform calculations about certain interactions, and that these calculations haven't been performed in as much detail before. So that, to me, that's more of that side is more theoretical than phenomenological. So yeah, choosing this particular topic on neutrinos and on beyond the standard model physics, this was something that happened once I was accepted into the program here, and I started talking to the different supervisors and finding out what they were working on. And that was when this project sort of synced up with me. I don't know how true that is in certain other fields, where sometimes I guess you do sort of propose your own PhD project, and if it's good enough, they take you, and that's what you work on. That's not the case so often in physics, because I think very few schools expect you to actually, maybe none, there should be none, expect you to come in knowing everything about what you're going to be studying. There's just too much content to learn, and that's stuff that you learn as you go along. So it's important to choose a project based on what you do know, even though that's limited, and then as it goes along, you have the freedom to adapt it as you learn more and figure out what it is that you actually want to do. That's my plan, certainly, is to learn as much background as I can, and once I know more, then I'll have a little more freedom to choose what direction to take this project. The other question I was asked was, let me find it. Still very new to the YouTube studio setup. Sometimes when I try to rewatch it doesn't show me all the comments. It shows sort of like as they happened, but as if I'm watching it again, which is kind of strange. there's a comment from Forrest. There we go. Okay, I found it. Forrest asks, I hope he doesn't mind reading his comment, but he did post it in a public forum, so I guess I can. I find myself wondering where my passions lie on a day-to-day basis. How do you stay focused and inspired every day? Where do you derive certainty in yourself and in your interests? That's a really good question, because that's definitely something I've struggled with too sometimes, of kind of trying to figure out physics is such a wide field, and anyone who's going into any field has to wonder, what can I really bring to this world, when there's thousands of other people already working on it, and some of them seem so incredible, and I'm a lowly student. It's hard to envision how you get from here to there. So I guess, how do I stay focused and inspired? I definitely don't spend too much time thinking about exactly what I want my career status to be in the future. I think that's necessary. You have to do that sometimes and sort of check in on, am I going down a reasonable career path here? Do I enjoy this? What kind of job am I gonna get based on what I'm doing right now? But it's possible to spend too much time doing that and end up, I think, being discouraged if there's other people doing things that you'd rather be doing, and you don't have the opportunity to jump right to that. I think a really good example is, I when I was a little kid, my dream job was definitely to be an astronaut. And I wasn't the only one, but I think at some point somebody sat me down and said, you can't just go be an astronaut. You have to go probably get a degree in, probably engineering is a good bet, maybe science. At some point you're going to have to do some real serious practice as a pilot too, and be in really good physical shape, and the list goes on. And I could totally see someone who wanted to be an astronaut hearing about that, and it's kind of conflicting hearing about all these things all these daunting tasks that you have to do when you're looking at someone who just already is an astronaut. You just want to be what they are. So I think that's analogous in physics, where you look at these people who are professionals, and you just want to be as good as they are and do what they do. But that would be just as silly as jumping in a rocket and assuming and magically knowing how to fly it, and having your body and mind immediately be ready for that. No, it's stuff you have to work at. So the stuff that focuses and inspires me, and the stuff that I derive certainty is a good way to put it, is from the much smaller scale work. I stay focused because I love what I'm doing. The destination is important too, but it's corny, but it's more about the journey. I do believe that when it comes to physics, that the stuff I'm studying, I really enjoy working on it. I'm excited when I'm working on it, and if you don't feel that about what you're working on, then you should work on something else. I do believe that you got to do something that inspires you, not just because of someday I could be that. That's a good goal to have too, but you should also ideally enjoy what you're doing in the moment, and as much as possible. And there's boring parts too. There's always some tedious parts too, but there's just enough interesting parts to make me want to get through the boring parts. I think there was one more question. Whereabouts are you living and studying? What do you find optimal about your less than common note-taking system? That is true. Any advice for undergrads? That's 3 different questions, but I'll answer them all. Where am I living? I'm living in London, and that's also where I'm studying. I'm not going to give too many details than that. I'm going to UCL, University College London. I'll tell you that. And I like London a lot because it's a city that has a lot of really incredible universities within a pretty small radius, interacting with each other. It's not hard to find people that are doing something, doing any topic you can think of. You can find students that are working on it here at one university or another, and I think that diversity is a really great thing about London. Um, as regards my note taking system, I everyone has a note taking system that works the best for them, and that ties into advice for undergrads too, which is figure out the way of taking notes and structuring your learning that works best for you, because it's definitely different for everyone. Um, Mine changes all the time. Like I started doing this LaTeX thing a couple years ago just because I enjoyed it, and I found that it was an efficient way to deal with classes where there were a lot of equations. Sometimes it got to the point where I can definitely. I mean, my handwriting is awful, as you can all tell. I can type it potentially faster than I can handwrite it, so that was a benefit for me personally. And I just like the idea of ending up with something clean that I can print out and look at later, and it also helps that it's on the computer automatically, and I don't have to necessarily scan in pieces of paper if I want to organize my notes later on. Um, it's searchable. That's a nice thing that you don't get with handwritten stuff. But there's disadvantages too, which is anything with diagrams is really hard to do. Some classes, the equations are just too complicated to type, for me personally, to type accurately. Like when I did QFT last year, some of the equations just get so lengthy. You're not saving any time by trying to type them, and in fact, I think it can, in that case, it can be distracting. I find it most beneficial in classes where it's mostly just text and you're sprinkling in some equations. Uh, Other advice for undergrads. Oh my god, I could go on and on about that. I will do some episodes at that point. When I've had some more time to think about what I want to say. Uh, General advice: explore as many different topics as you can throughout your undergrad. Don't feel limited to whatever your major is, because, well, first of all, that can change. But even if it doesn't, there's so many more important things that you can learn than just what's in your major. Um, I and I'm a hypocrite saying that, because I did a physics major in undergrad, and here I am doing physics. That worked out well for me, but that's not always the case, and it's oftentimes what seems to determine people's career paths is not their thing that they studied as their major in undergrad, but the other stuff that they studied. Um, what class they took that they didn't really think they were going to take, but then they ended up loving it, or a minor that they added on that just quickly became their passion, is something they didn't know about before. I've heard those stories so many times from so many different people. Um, and I think my other advice is to interact with your professors on a personal level as much as you can. Don't, you know, going into the classroom and coming out of the classroom shouldn't be the only times that you see your professors in undergrad. Like, if you're interested in what someone does, send them an email, and if they don't answer, show up at their office and ask them questions, and bug them, and you will become their friend that way, because not enough students do that, so you immediately stand out. I got almost any summer research I've done, I got that way, just because I was talking to different professors, and I was able to convince them to let me work on something over the summer, or they knew that I was interested in something and recommended me to somebody else who was looking for a student. I mean, it's a good way of getting your name out there. And that's all I can think of right now. But I will definitely do more of a advice for undergrads session at some point. I'm gonna add that to my list too. And ooh, another sort of meta advice is definitely, go to other grad students that you know for advice too, because everyone's going to have a different perspective. If I do an undergrad advice session, I'll definitely have other of my grad student friends chime in, because I'm sure a lot of us have different experiences and different perspectives. So I think that's all I'm gonna do today. Thanks to everybody who watched. Thanks to everybody who watches this after the fact. And UCL, please keep funding me. Bye, everyone.